two unsupervised learning concepts. One is clustering, and the other would be dimensionality reduction, in which we'll only briefly touch on principal component analysis. So unsupervised learning, contrary to supervised learning, trained on historic data of which the inputs are known, but the outputs are unknown. So we're not training with a specific outcome in mind. The algorithm finds patterns in unlabeled data without prior knowledge of the output. Clustering can help businesses group their customers based on demographics, behavior, and purchase history. This enables targeted marketing campaigns, improving customer satisfaction and increasing sales. So basically, we're going to cluster customers based on their, well, either behavior, which could be purchase history, or interests, and so on. And then in the future, we could target clusters of customers with specific marketing campaigns, for example. There are, of course, multiple use cases for that. In computer vision, clustering can be used to categorize images into different groups, like scenes, objects, textures, based on visual features such as color, texture, or shape. Recommendation systems, clustering can help recommend products or services by grouping users with similar preferences and interests. This leads to more accurate and personalized recommendations. So this is slightly different than just customer segmentation. And I think I'll make an extra video on recommendation engines using matrix factorization. The matrix factorization stuff. Let's see, clustering customers by spending habits. Banks and credit card companies use clustering to segment their customers based on spending habits, enabling them to offer tailored financial product services and interest rates. Then there's always a medical case, use case as well, grouping patients with similar symptoms, disease progression, or treatment outcomes. This facilitates more accurate diagnoses, targeted interventions, and improved patient care. Predicting movie genres. Okay, I think we got the ID. Personalized education. Grouping students similar learning styles, based interests. Again, to create tailored trajectories. Okay. We are going to be doing a exercise. I did add a lot of links down below, videos about principal component analysis, which is a anomaly detection would be another application within the unsupervised learning space. We may touch upon that in another video. Let's cover dimensionality reduction and principal component analysis briefly, since that will be used in the exercise below. So dimensions or features, that's kind of a synonym in the machine learning space. We already saw in the regression with the regression models that we didn't need all of the features to get to a qualitative model. There were features, if you remember correctly, with the correlation matrix, features that don't really contribute or attribute anything to the thing we want to predict. So we could just drop those features, and by doing that we keep the most essential features, and to hopefully have a qualitative model as outcome to train on, essential data to train on to result in a qualitative model. Now, there are definitely other types of ways to do dimensionality reduction, or feature selection is what I was actually talking about. So select a subset of the most relevant features. Yeah, we did that by hand. There's also ways to measure the feature importance and then maybe throw away the ones that don't seem to be too important. So what's the problem with dimensionality? As the number of features or dimensions increases, the volume of the feature space grows exponentially, which becomes more computationally expensive, while a lot of the data or the features can be regarded as noise, which means non-essential data, just like garbage data that we don't need. So that's what I was saying here: improve model performance, simplify models by reducing redundant or irrelevant features, reduced noise sensitivity, filter out noisy dimensions, leading to more robust results. So data quality, let's say. Data visualization, reduce dimensionality for easier visual representation. So if you remember correctly, something else I touched on, the regression was, this polynomial was taking features to a higher order. Linear regression, let's see. No, that's not in here. I can't find the exact picture, but I basically wanted to show that hyperplane, like once you have more features, like with the simple visualization, always have like an y-axis and an x-axis and just two features, which could be color and acidity or something like that. But every time there's an extra feature, you would basically have to draw an extra axis, which the third one would be 3D, so the depth, and then maybe not one more feature becomes 4D and so on, and you start working with these hyperplanes instead of simple dots on the visual in a 2D representation. Principal component analysis is what we'll be using in this exercise as a pre-processing step of the data before we do clustering itself. Let's see, a linear method for finding the directions of maximum variance in the data. I added some links down below with some video explanations of principal component analysis, this short, for example, and you will see how they reduce dimensionality with an easy visual. There's also other ways of dimensionality reduction using autoencoders, which are neural networks that can learn to reduce dimensionality and reconstruct the input data. It's a bit like compression, something like that. Specific use cases in image recognition, reduce dimensionality using principal component analysis and TSNE or autoencoders to simplify image representation and improve model performance. PCA has a specific techniques, eigenvalues, eigenvectors, eigenfaces, for example, for face recognition, which you can also learn more about in the links below. But like, I think I already tried to explain that in image recognition. I think even in the previous video in the decision trees, where we were working with images and basically have a resolution of an image, which could be like, it could be a large image, 512 width, 512 height. The first thing you could do is, scale it to 28 by 28, for example, or 32 by 32. And then you could grayscale it, because maybe the color of the pixel doesn't really contribute much to just handwritten digit recognition, for example. And then you can, of course, go even further, reducing dimensionality, and so to only keep the essence of the data that is needed to do, for example, image classification, recognition, and to speed up the training process and hopefully improve model performance altogether and reduce the training time and so on. So it's kind of outlined how it works more or less, but I would recommend to watch some of the videos if you're really interested. They explain that a bit better, what exactly this variance is and so on. Standardization. It's basically to lower all the feature values between a value of between 0 and 1 instead of 0 and 255 or 0 and whatever the maximum feature value can be. Also for improved training and so on. These principal components should be the most important features. So, and then it says limitations assumes linearity, which it's not always the case. If I'm not mistaken, what I wanted to show on the SVMs can happen. Well, it's actually more with clustering, but if your data looks more like this, then you can also do some kind of kernel trick to decide clusters. So here are the links. PCA short, StatQuest has a few short videos on it, but also one very in-depth about the variance to calculate these. Eigenvector, eigenvalue, eigenfaces, those are all concepts you can learn more about. So now we'll be using the k-means algorithm for clustering and our exercise below. And here it states principal component analysis is often used as a pre-processing step to reduce dimensionality of the high-dimensional dataset before applying k-means clustering. This is known as PCA-based k-means or dimensionality-reduced k-means. So in real-world data sets, there could be hundreds or thousands of features, which leads to complications. Okay, PCA helps to reduce noise and correlation between features, which can improve stability and accuracy. K-means algorithm. Use PCA to reduce the dimensionality of high-dimensional data sets by selecting a subset of the most informative principal components or features. The most informative, that's what I meant, the most important features. And then that's basically makes up the essence of the data, let's say. That may be a very scaled down and grayscaled version of some kind of image, and so on, which may only, we can see that the neural networks, maybe with the convolutional neural networks, gray image, which mostly keeps the diagonal lines or some kind of structure that is most important to make up the image. That's enough information to train these models on. It's basically a bit the same concept. Convolutional neural network is going to do that differently, of course, with filters, but we may see that later, if we ever get there. Okay, so we're not going to be choosing the outcome since it's unsupervised learning, but we can play around with the k variable and k-means, which means the amount of clusters that we would like to see. How these clusters are made up is completely out of our hands. So that's why it's unsupervised learning. Okay, so this exercise from the Microsoft samples. Let's go over that. This is about customer segmentation. You want to identify groups of customers with a similar profile, so you could target them afterwards, like with marketing campaigns per customer group and so on. So the problem to solve is how you identify different groups of customers with similar profile and interest without having any pre-existing category list. So we don't have the categories to classify on, let's say. So we're not doing classification because your customers are not labeled, so you cannot do that. Yeah, which means it's not like the customer already has a label of which group or cluster it belongs to on beforehand. You just need to make groups, clusters of customers that the company will use afterwards for other business purposes. Okay, that might be more practical already. This is about wine data, it seems, which contains historic, well, it contains offers and deals, part of marketing campaigns. So a marketing campaign will be selling some kind of offer or discount or deal. Well, discount deal is the same, almost. And then plus the purchases made by customers. So here we see different offers, which were in. So in the campaign in January, we had this offer, which could be like a discount on this Malbec wine when you purchase these, I guess. And there's different offers, different discounts, and so on. Then we have customer transactions, so which people actually bought wine using these discounts. And that is then summarized later on. So Smith has purchased once using, well, you purchased some wine using offer 2, but I assume this is the same Smith, this is only the last name. He or she also bought wine on offer 24, which is a different campaign. In a different campaign, Johnson has done 3 purchases on different offers, and Williams. Okay, let's see. Then they continue to explain more or less how the k-means algorithm needs to be configured. Well, so you have, it's not going to decide the optimal number of clusters, so we'll have to pass the amount of clusters we'd like to see. You can always adjust it if the result isn't great. K-means minimizes the distance between each point and the centroid of the cluster. So we'll get 3 clusters, 3 centroid points. The rest should be in the distance around that. All points belonging to cluster have similar properties. So that's the point. Let's see. So now it's explaining about PCA, how we're working with 32 features. We're going to reduce that to a 2-dimensional space. It's called dimensionality reduction. Okay, so the data pre-processing, they did that for us already. It's basically, they have a table with offer ID, campaign discount, and so on. And they will only take the offer ID. Let's see. After pre-processing, the point is they end up with all the offers. So 32 offers, 31 offers, and the last name. And then these should be the amount of purchases in that offer. Let's see, some. Oh. And the rest is just, yeah, here we're going to do that principal components. Make it, add an extra output column name, BCA features from features, which are 32 features loaded here. And then the last name is the label, is the 32nd column. Rank 2, so we're going to reduce it to 2 features. One hot encoding for the last name, which means we're going to encode the text values, like what was it, Smith and other last names, into numeric representations. And then we use a k-means trainer to train a model using the features, and we define the k value, which is 3 numbers of clusters. So let's go to the notebook. Basically did that. First install the packages, use everything we need, the ML transforms, trainers, data, and so on. Scotplot for visualization, initializer ML context. We load the data set, which is, let's see, so basically those 32 features, well, 30, yeah, and last name. We model it, input data, we model the prediction or the output of the model, which is last name, score, which is distance, select the cluster ID, so this will be predicted by the model, the distance as well. BCA features location, this is basically X and Y location on the feature space, if I can say it like that. This distance is from the centroid. Let's see, loading the data. Of course. Then we're doing the PCA and the one-hot encoding. The trainer with 3 clusters. We fit the pivot data on there, which is basically just loading the dataset that I just showed you. Let's see. Transform data view, maybe we should take a look at that. Then the metrics. Let's first take a look here. Input schema, output schema, source. Let's have a look. Input schema. Last name key vector. Last name key by the one-hot encoded values normally. Let's see. Categorical slot ranges, PCA features vector of 2. Let's see, these are just the types. The original types. And then we get some metrics. Let's see, average distance. I'll have to come back on those metrics because it's not too well explained in the Microsoft sample docs either. So I'm just going to assume the average distance between the centroid and the other data points in the cluster. And then this Dave is bound index. I have no idea what that means, so I will quickly look it up before ending the video. From the transformed data view, which is okay after training. Yeah, it's basically almost the same that we see here. Predictions, outputs are collapsed. Why? Okay. And that's what we'll get. So selected cluster ID, that's predicted by the model. Then the location, the X and Y values, and the last name. X and Y values in the now two-dimensional space. And then the distance, which is I have to look that up. Those are 3 values from the centroid. A little different. Last name Lee. Here I group and order them. Basically have 3 clusters. This is cluster 3. Last name Brown. Distance, location. Okay. Let's see. Then we're just going to visualize it, and that's what we'll get. 3 clusters with the X and Y values, which are in the location property, X and Y. and then we just assign it a color per cluster. You do see some overlap in here between red, blue, and green. It's mostly red, which is overlapping with the others. Maybe you can separate blue and green better. So what do we have now? Supposedly 3 clusters with 3 groups of customers that purchased on certain campaigns. And now we should be able to target those groups individually with other similar interesting campaigns, I assume. Let's now try 2 clusters and see what that gives. Of course, it should give 2 clusters, but let's see if it makes this all blue, for example, and then just a little green, or whatever happens. Yeah, that's kind of what happens, although a bit more like that. Let's see what happens with 4 clusters, play around with it until you get like a proper separation. Well, 4 clusters doesn't seem to be really separate. Yeah, 1 cluster we don't need to try, there's no point in that. So yeah, it's either 2 or 3. Let's try 2 again. Two seems to be quite shifty. Maybe it's not able to make 2 clusters. 3, but something's happening. Let's see what's up. This is not what we started with. A bit strange. I've done it a couple of times with 3 clusters, yet nothing. Yeah, it was always kind of similar. Now playing around with it, it seems to shift quite a bit. It seems to make slightly different clusters each time. Well, the first one was kind of looking like the example, but sometimes it can look way off. This seems to look like, except for one point, one red point, seems to look quite like the example, just this one. Let's see. I can just run it all a few times. Get slightly different clusters. Ooh, but sometimes it seems way off. Well, this is a nicer one, I guess. Just a few red, blue, and green. Okay, let's return to the metrics. Okay, let's see. K-means clustering metrics. When evaluating the performance of K-means clustering algorithm, several metrics can be used to assess its effectiveness. Okay. These seem to measure the quality of a cluster given a K value, which is the amount of clusters. Then we have this one, Davis-Bouldin index, DBI, Bouldin. Is a metric used to determine the optimal number of clusters for a given dataset. DBI is based on 2 components. Similarity measures the similarity between centroids. Separation measures the separation between centroids. For each centroid, DBI calculates its average distance to all other centroids in different clusters. The higher the value, the better the cluster separation and the worse the clustering quality. The better the separation, the worse the quality. I think the better the separation, the better the quality. Or what? The lower DBI is the better clustering quality. Then the average distance, which measures the average distance between each centroid and its corresponding cluster points. So inside the cluster, this gives an idea of how well the centroid represent their respective clusters. So this should also be low. This is more inside of the cluster. We're getting a Davis-Bulden index of 2.3 and average distance of 2.2. I assume if we do 2 clusters or more clusters, these values are going to get worse. So let's do 4 clusters. Oh, that seems better, but we'll lower. Clusters don't look too bad. Let's see if we can. Oh, this has a lot of overlap, these two. Let's see what the. So now this Bulden index is a bit higher than before, and there's a bit more overlap between different clusters. So like 10. Oh, scores are lower. See what happened here. Hey, I don't have 10 colors here. The values, Davis-Bulden index and the others seem lower, but doesn't seem like well separated clusters. Two. Let's see. It's a higher Davis-Bulden index and average distance. Well, average distance may be logical because now we only have two big clusters with half of the amount of the points instead of having very small clusters with just a few dots around it. So maybe it makes sense that the average distance is a bit higher. And then Davis-Bulden index, the distance between the centroids of the different clusters. But this says the higher the value, the better the cluster separation, the worse the clustering quality. So maybe a good separation, but worse quality because there's maybe just too many points in the cluster, which these top ones may not really represent the rest of the cluster, vice versa. Okay, I'm going to end our suffering here. This was K-means clustering. You can find the code used for these videos on the members only section on casco.com/members. You can easily become a member to access that code. You go on a post and you have the unlock here button. If you are a member, you will be able to download it. Or you can find them on my Patreon. Don't forget to like and subscribe to the channel for more. I'm aware that we're going over too quickly and I'm not going in depth enough on all these topics. Just show you multiple to machine learning, and then it's up to you if you're interested to dive deeper in all of these things. Hopefully we'll get to real use cases, real data, and so on.